The whole universe was in a hot, dense state, and nearly 14 billion years ago, expansion started. Wait, the Earth began to cool, the autotrophs began to drool, the Neanderthals developed tools, they built a wall, they built the pyramids, math, science, history, unraveling the mystery that all started with the Big Bang. I hope you're impressed by that. I'm going to stop now. I do know the rest of the song. We're going to do about Big Bang and redshift today. Let's go. So you need to be able to, everybody needs to be looking at that level 4 and going, yep, okay, cool, can do that. State the wavelength of a wave is changed by the movement of the source. Galaxy shows redshift because it's moving away from us. State the galaxy is moving away from us and describe how the wave is altered. Identify red or blue shift is grade A. Everyone can do this. It's not a complicated topic. It's just about using the right words. And explain how we use redshift to help support the Big Bang theory. So let's go. So our galaxy, the Milky Way, billions of stars, it's 100,000 light years across. That means it takes 100,000 years for light to travel from one side to the other. Now, to bear in mind, it takes 7 minutes or between 7 and 8 minutes to light reach us from the sun, which is a really long way away. It's huge. So if we were looking across our Milky Way at a planet, or someone was looking at us, they'd probably be seeing Earth millions of years ago. Billions of galaxies, obviously, in our universe. It's sort of the shape of this beautiful diagram. So yeah, huge, and lots of galaxies and super galaxy clusters in our universe. Now, we study them using telescopes and photographs, and the furthest known galaxy is 15 billion light years away, so it takes 15 billion years for the light to reach us. So when we're looking at it, we are looking at it 15 billion years ago. So how do we study? We just look at the light that is being produced by celestial bodies, so something in space, and we can determine what it's made from, what light it's emitting, what stage of life it's at, based on chemical and thermal emissions, really. And this is where redshift comes into it. So what we're looking at on the spectrum of colour will tell us about galaxies and stars. So these are things that we do know. So if you look at the top right of the screen, you can see the spectrum of light. So we know that when we've got red, orange, yellow, green, blue, indigo, and violet. We know that on a rainbow, red always travels at the top and violet always travels at the bottom. Now, if you look at a rainbow, you can see that red is always at the top. So therefore, we can deduce that red has the longest wavelength of light, which it does. So you can see here the wavelengths are longer and these wavelengths are shorter and a higher frequency. So that's an important thing to remember when we're looking at light. Red has a longer wavelength than orange, which is longer than yellow, which is longer than green, etc., etc. So the colour of light is dependent upon its wavelength. So if something is emitting red light, it means it's emitting a longer wavelength than something that is emitting violet light. Okay. So this is called the Doppler effect when we are looking at changing the shape of waves. So if we take a wave and we stretch it or squash it, we can change the colour. So on the previous slide, if I squash the wavelength of red, I can make orange. And it's the same with sound. If you listen to ambulances when they go past, as it moves quicker, it squashes the wavelength. And so that's why we hear this when things go past us, because the wavelengths are being squashed and stretched. In the same way, when things break the sound barrier, there's a huge crack because they're getting through all of these compressed waves. Okay, so as waves are stretched, they will become deeper sounds, and as they are squashed, they become higher pitch sounds or higher frequency sounds. And it's the same with light. If you squash light, it will be blue, or it will get bluer. And if you stretch it, it will become redder. More red. That was bad grammar, I think. So when the stationary sound has a constant wavelength, it'll be the same pitch. So if we're thinking about a motorbike, it'll go, it will be like a constant pitch. As it moves towards us, the wavelength decreases and it becomes higher pitched. So it'll go, and then as it moves away, they increase in length. So it'll go, or when things go past us. It's the same with if you listen to a police or an ambulance siren, they go, like they sort of go higher and then go lower. I'm making so many weird noises today, sorry. Okay, it's the same for stars. So stars constantly produce light. White light is obviously a mixture of all of them, and each colour has its own wavelength, but changes how it's looked when they're mixed together. They make white, obviously. So you can see here that we've got much longer wavelengths, shorter, shorter, shorter. So our sun is always the same distance from us, and it's constantly sending out each different colour mixed together to make white light all of the time. This is just another picture of the light spectrum, but you can see here that this has a wavelength of 400 nanometers, so that's 1/1000th of a meter, and this is 700 nanometers. And this is the visible spectrum of light, and remembering that a nanometer is 1 × 10⁻⁹ meters, so very, very small. Stars from distant galaxies emit the same light as from our stars. So let's say this looks yellow and it's emitting that light. And we can split it into the spectrum and analyze it. However, if we have light from a distant star, can you see that these have shorter wavelengths than these? Which means that if it's moving towards us, or away from us. So here we've got something moving towards us. So the light rays have been squashed, so it's appearing more blue. And this one is moving away and it's appearing more red. So I like to do this experiment with students where I get them to get a balloon. So if you have a balloon, I'll do a video on this, and you draw a galaxy, and we're going to call this galaxy, oops, a daisy, we're going to call this galaxy A. Okay, and then you draw another galaxy, and I'm going to call this galaxy B. I'm going to draw a wavelength in between. Okay, if I was to blow up that balloon and make it bigger, galaxy A would look bigger, so would galaxy B, but this wavelength would also be stretched, and the longer the wavelength, the more red it looks. So if I was sitting on galaxy A and galaxy B is moving further away from me because the universe is expanding, that means that it's going to appear more red. So if it did appear orange, it's now going to appear red. If it did appear green, it's going to now appear yellow. So you can see here, this is just like the spectrum light. So this galaxy, we'll call this galaxy B while I'm looking at it on day 1, and then day 300 or whatever, it looks slightly less blue, a tiny bit more green. We know that it is moving towards the red end of the spectrum, and we would call that redshift. If galaxy B was moving towards me, it would be going in the other direction, and so everything would appear to be moving towards the blue. So, light is emitted from stars or another source as a continuous spectrum. As a gas cloud absorbs specific wavelengths corresponding to the energy levels of the atoms, the absorbed light appears as black lines on the spectrum. So any light that's being emitted that is absorbed comes up as black lines. Okay, so you might get in the exam, you might get one of these spectrums, and some will be emission spectrums and some will be absorption spectrums. So the one we were just talking about that we get from galaxies tend to be absorption spectrums. So where the colours have been absorbed, you'll find missing dark lines, but you'll see that they match the emission spectrums if they were being just collected as their emission. So again, just so you're aware, if you were to see this one, let's say it was here, if you saw the lines drawn like this, they're getting closer to the blue end of the spectrum, therefore we would say that's blue shift, and if they went the other way, it'd be red shift. So here we've got the unshifted galaxy here, and here we've got redshift because they have moved here, which means that those galaxies getting further away, so the light has been stretched, and this one is coming closer to us, so therefore it's been blue shifted. Okay, so these are things that you might wish to pause, or you're going to need to pause to do your answers. So pause those now. Okay, so let's go through them. Why can white light be split into different colours? Because the colours have different wavelengths. And if you can't remember, the wavelength is measured in meters, and it has this symbol or this symbol lambda. What's the difference between blue shift and red? What's the difference between blue and red light? Red has a longer wavelength than blue light. What happens to a wave if the source is stationary? Nothing. What happens to a wave if the source is moving away from you and towards you? So if it's moving away from you, it's red shifted. And if it's moving towards you, it's blue shifted. How does this link to stars? Well, we are observing galaxies, and if we observe the galaxies doing redshift, it means they're moving away, and if we observe blue shifting happening, it means they're moving towards us. What is the Doppler effect? So that is the effect of sound waves being stretched or compressed depending on an object is moving away from you or towards you, and so therefore there's frequency changes. What can you tell about the movement from the source? Well, if it is moving towards you, then we get higher frequencies or a higher pitch, and if they're moving away from you, they get a lower pitch. Describe what an absorption spectra from a stationary star looks like. So it looks like the spectrum of light. Let's say that's red and that's blue, with black lines where the colours it's emitted are being absorbed by a cloud of gas. Describe what an absorption spectrum from a moving star looks like. Well, if it's moving, then it means that the absorption lines will change position. What can this tell us about the movement of a star, whether it's coming towards us or moving away from us? Simple, really. Okay, what can we learn from redshift? So a couple of things. It tells us that the universe is expanding. This was discovered by Edwin Hubble in 1929. History fans, what happened that was a big deal in 1929? It was the Wall Street crash. That was bad times. It's when the big depression died. So he worked out that the light from distant galaxies was red shifted, which means that they were moving away, and so they were appearing more red. The further away from the Earth, the bigger the red shift. He concluded that distant galaxies are moving away from Earth. The greater the distance, the greater the speed of recession. So what he's saying is if we're here, excuse me, pen work. If we're here, okay, and I've got galaxies here, they are moving away from us, and the further away they are, oh, here's my balloon, here we go. So he said that the universe is expanding relative to us, so he made it clear that the Earth is not special. All galaxies are getting further away from all of the other galaxies, because obviously if you're in this galaxy and you're observing that galaxy, it looks like that galaxy is moving away from you, but you're actually moving away from each other. Okay, the whole universe is expanding. All of the distant galaxies are getting further away. And this is evidence for the Big Bang Theory. So the Big Bang Theory is that all energy and matter on Earth started at a single point and it moved outwards in a big explosion. And the fact that we're still moving outwards from that single point is really good evidence for the Big Bang Theory. Ta-da! Not the only theory, just so you're aware. Einstein didn't support the Big Bang Theory, but it is the best theory that we have based on evidence that we have. He believed in something called steady state theory, which was basically that, like, if this is our universe, it's the same as it's always been, and it changes. People aren't sure what's going to happen when we expand to a certain point. They believe there's going to be something that happens called the big yawn, which is where we keep moving outwards and very big, and eventually we're going to run out of fuel and the universe is just going to go dark. The other theory is called the Big Crunch, which is where it'll keep moving outwards and outwards and outwards, and then it's basically going to elasticate back and smash into that one small point, and then it's going to go out again. Very interesting. So 4 billion years from now, our galaxy, the Milky Way, will collide with our large spiraled neighbour, Andromeda, 300 millimeters per second. So 4 billion years from now? It's quite a long time. So closer galaxies are just slightly different. They're not necessarily, we're moving into each other's pathways, I suppose. I'm going to add a little cheat to go on there, or a doodle task, so you can work through that. So I hope that was okay. I hope that was helpful. So essentially, redshift is evidence for the Big Bang Theory. There is more evidence for the Big Bang Theory, like cosmic background radiation, and that's when you turn your radio on, it goes, that's radiation from a huge explosion that happened. That's a bit of knowledge. See you later. Bye.